You've seen them, right? Those absolutely colossal cylindrical storage tanks on the side of the highway. I mean, these things can hold millions of gallons of product. But if you ever wondered what happens when you need to move one or even rebuild it, well, you don't just call up a regular construction crew. Nope. You bring in the engineers with a very, very specific rule book. Okay, let's get into it.
I mean, seriously, think about that for a second. This is not just some big bucket. It's a precisely engineered vessel that has to handle insane amounts of internal pressure, not to mention all the forces of nature. One tiny mistake, one little miscalculation, and the consequences could be absolutely catastrophic. So how on earth do they get it right every single time?
Well, the secret is a document called API653. Now, that's the official standard for tank inspection, repair, alteration, and reconstruction. But listen, this is so much more than just a set of guidelines. It's the high-stakes engineering playbook. It's what ensures these giants can be safely taken apart, moved, and put back together to start a whole new second life. So today, we are cracking open that rulebook, and we're going to look at the key design rules from Section 8. We're going to see exactly how engineers use this guide to turn a truly monumental challenge into a safe, predictable process. Yeah, there is absolutely no room for guesswork here. Reconstructing a tank is all about math, material science, and just meticulous attention to detail. Every single part of the plan, from how thick the steel walls are to the exact type of welds holding it all together, it's all dictated by these rules. All right, let's start with the most obvious part, the one you can't miss. The massive steel walls that make up the tank's shell. They have to be strong enough to hold back the immense pressure of all that liquid inside. But how strong is strong enough, especially for a tank that's already been in service for years? The rule book lays out a super clear 3-step process. First, you can't just assume anything. You have to go out and physically measure the actual thickness of those steel plates. Second, you have to factor in the specific gravity of whatever's going inside. Now, that's just a fancy way of talking about its density. For example, molasses is way denser and heavier than water, so it's going to push a lot harder on the walls. And finally, you calculate the maximum stress that specific type of steel can take. You put all that together and boom, you have your safe maximum fill height. And this is where it gets really smart. The engineers build in a critical safety margin. The rule book says, okay, for a one-time test fill with water, that's called a hydrostatic test, you can push the steel a little harder. But for the tank's normal day-to-day operational life, the stress limit is lower. This creates a buffer, right? A clear difference between the absolute maximum the tank can handle and the maximum it's allowed to handle day in and day out. It's all about that safety buffer. And get this, the engineers have to be fortune tellers, kind of. They know that over decades, a tiny bit of the steel is going to corrode away. It's just what happens. So they add something called a corrosion allowance, a few extra millimeters of steel thickness from the very beginning. It is literally like planning for wear and tear before it even happens, making sure that tank stays safe for its entire life. You've heard this saying, right? A chain is only as strong as its weakest link. Well, on a giant steel structure like this, that weak link is almost always the welds. These are the seams that stitch those massive steel plates together. So you better believe the rulebook has a whole section just on making sure they are absolutely flawless. I mean, just listen to that language. Complete penetration and complete fusion. That is not a suggestion, it's an order. It means any new weld made when they're rebuilding has to be perfect. The welder isn't just gluing the edges together, they are literally melting the two plates so they flow together and become one single, seamless piece of steel. Anything less could create a microscopic weak spot that could fail under pressure. Okay, so that's for the new welds. But what about the old ones that they're not replacing? Well, the rules are different there. Those existing welds are basically grandfathered in, as long as they met the safety standard that was in effect when the tank was first built. And that's just a really practical and smart approach, right? Anything new has to meet today's top standard, but anything that's already there is judged by the rules of its own time. All right, so the tank is strong enough to hold all its contents from the inside out. But, it doesn't exist in a bubble. It has to stand up to the real world, facing down some pretty powerful forces of nature. And of course, the rulebook has that covered too. First up, wind. And yeah, I know what you might be thinking. Wind against a massive steel structure? But a strong, sustained wind pushing against that huge surface area can create an incredible amount of force, especially if the tank is empty. So to fight back, the standard says you have to check the wind girders. Those are the reinforcing rings you sometimes see on the outside of tanks, and make sure they're up to modern standards. Then, engineers run a ton of calculations to make sure the whole structure is safe from something called wind-induced buckling, which is basically the engineering term for the wind trying to crush the tank like an empty soda can. And next, an even more violent force: earthquakes. A tank full of liquid is especially vulnerable when the ground starts to shake. That sloshing liquid can create these huge, unpredictable forces, basically a tidal wave inside the tank. This is exactly why the rebuilt tank has to be checked against the current seismic standards for its new home. This could mean they have to add thicker steel plates at the bottom, or, and this is a big one, install massive anchor bolts to literally strap the tank to its concrete foundation, even if the original design never had them. It's all about upgrading safety to what we know is required today. So when you take all these individual rules and put them together, the rules for the shell, for the welds, for wind, and for earthquakes, you don't just have a collection of regulations anymore. What you have is a complete blueprint for safety. Let's just do a quick rundown. The shell thickness, meticulously calculated for strength and for future corrosion. The welds, held to the absolute highest modern standard if they're new, and their original standard if they're not. And the whole thing? It has to be proven to handle the wind and earthquake risks of its exact location. Every single piece works together to create a system where safety isn't just a hope, it's a mathematical certainty. So the next time you see one of those huge tanks, you'll know it's not just a big steel can. It's a testament to this incredible, invisible rulebook, this hidden layer of engineering that's constantly balancing these immense forces. It kind of makes you wonder, doesn't it? What other unseen standards are out there, quietly holding our world together? From bridges to airplanes to the entire electrical grid, our safety relies on these blueprints of precision, all just waiting to be explained.